In our last lecture, we have studied the concept derivatives of an inverse function in the topic differentiation, in which we have studied the existence of inverse function. Means inverse function exists if the given function is 1 1 as well as onto. Also, we have studied the concept that how to find out the derivatives of inverse function. Means in that we have studied one theorem related to uh, the derivatives of an inverse function. Today we are going to discuss the concept the derivatives of an inverse trigonometric function. So in particular we have to study the inverse trigonometric function, and in that we have to study that all inverse trigonometric functions exist on the basis of following conditions. Means conditions means the original function means must be 1 1 and on 2. So what are the conditions for the existence of inverse trigonometric functions? That we will study by this table. Okay, so see here, first function as a standard function means standard inverse trigonometric function. That first function is y is equal to sine inverse x. Now this is the inverse of sine function. Okay, so we have to decide its proper domain. So domain is close interval minus 1 to 1, and codomain is close interval minus pi by 2 to pi by 2. Okay, so specifically in case of inverse trigonometric function, we have to select the domain as close interval minus 1 to 1 and codomain as close interval minus pi by 2 to pi by 2. You just remember this. Okay. Second function is y is equal to cos inverse x. It is an inverse of cos function. So see the domain. Domain is close interval minus 1 to 1 and codomain is close interval 0 to pi. Remember this. Third one is y is equal to tan inverse x. This is an inverse of tan function. So what is its domain? See here, R. R means whole real line is the domain of tan inverse x, and codomain is open interval minus pi by 2 to pi by 2. Open interval means minus pi by 2 and pi by 2 are not included here. Fourth one, y is equal to cot inverse x. Now the domain of cot inverse x is set of all real numbers, and codomain is an open interval 0 to pi. Similarly, fifth one, y is equal to sec inverse x. Then its domain is modulus of x greater than or equal to 1. Now modulus of x greater than or equal to 1 means x is greater than 1 and x is less than minus 1. Okay, okay, remember this. And codomain is close interval 0 to pi and minus pi by 2. Minus pi by 2 means we have to exclude pi by 2 from the close interval 0 to pi. Okay, because sec inverse is the inverse of sec function, and for sec function sec pi by 2 is not defined. So for that we have to remove pi by 2 from it. And sixth one, y is equal to cosec inverse x. Its domain is modulus of x greater than or equal to 1 and codomain is close interval minus pi by 2 to pi by 2 minus 0. 0 is excluded, okay, from that interval. So all of you remember what are the standard inverse trigonometric functions. So these are 6 standard inverse trigonometric functions, and depending on the condition, means on the basis of the existence of inverse of any function, we have to select the domain and codomain. Means before defining sine inverse x, you must know the domain and codomain. So you just remember this as a basic knowledge. Our main point is how to find out the derivatives of all these standard inverse trigonometric functions. Means in this lecture we have to study what is the derivative of sine inverse x, or what is the derivative of cos inverse x, so on like this. That is our main part. Okay, now one by one we will prove all the results, all standard results. Results means we have to find out the derivative of sine inverse x and so on. Okay, one by one we will study. So let us see first theorem. See here, if y is equal to sine inverse x, this is the function given to you, and the condition on that is, see, minus 1 less than or equal to x less than or equal to 1, means x lies between minus 1 to 1 and y lies between minus pi by 2 to pi by 2. So these are the proper condition for the existence of sine inverse x. Then prove that the derivative dy by dx is equal to 1 upon root of 1 minus x square. Okay, where modulus of x less than 1. So that we have to prove. So see the proof properly. So here the given condition is written like this, that is y is equal to sine inverse x, and condition on x and condition of y are given to you. Now to get the derivative of y is equal to sine inverse x, we will write it as x is equal to sine y. So see here, just we have written this function in this form, x is equal to sine y, because y is equal to sine inverse x. Now we have to differentiate this function, means this is x in terms of y. Okay, so we have to differentiate this with respect to y. Remember here, differentiate with respect to y, not with respect to x. Remember, because it is sine y function. First of all, take a note on this. Okay, so differentiate with respect to y. So what will you get? Dx by dy, that is equal to d by dy of sine y. Now we know that d by dy of sine y means derivative of sine y with respect to y is just a cos y. Okay, so we get dx by dy is equal to cos y. So this is the derivative of x is equal to sine y. Now for further adjustment, we will follow the steps like this. This cos y can be written as plus or minus root of cos square y. Just we have taken the square and then root, so you will understand this. So plus or minus root of cos square y. This can be converted into this form, plus or minus cos square y can be written as 1 minus sin square y. Then next step, we get dx by dy is equal to plus or minus root of 1 minus x square, since sin y is equal to x or x is equal to sin y. Just replacement here. So already here we get the derivative dx by dy is equal to cos y. We converted it into this form, plus or minus root of 1 minus x square, by this adjustment. Okay, now we have to decide whether we have to take it as plus or minus. Okay, so depending on this condition, means original derivative is cos y and condition of y is y lies between minus pi by 2 to pi by 2. So what is the condition? So here, depending on the condition of y, cos y is positive since y lies in first or fourth quadrant. See, minus pi by 2 less than or equal to y less than or equal to pi by 2 means it is first or fourth quadrant. You know that up to pi by 2 it is a first quadrant, and minus pi by 2 means the direction is clockwise direction. if you take that clockwise direction, then up to minus pi by 2 it is fourth quadrant. So remember, up to pi by 2 first quadrant and up to minus pi by 2 it is a fourth quadrant. So in first or in fourth quadrant, cos y is always positive. So this derivative, original derivative, is always positive. Here we get it as plus or minus by this due to this adjustment. But further we have to take that plus or minus. In place of that we have to take it as plus only. So I have shown particularly here plus sign. So just we can write it as root of 1 minus x square. So remember, depending on the condition of y, we have to decide whether it is plus or minus. Here we have to take it as plus. So it is written as root of 1 minus x square. So this is dx by dy. Now this is the derivative of this function. X is equal to sine y. But we have to prove the derivative of y is equal to sine inverse x. Now it is the inverse function. So we, by that theorem, we know that dy by dx means we require dy by dx. So dy by dx is equal to 1 upon dx by dy. Okay, you know this. So by that relation, hence we get dy by dx is equal to 1 upon root of 1 minus x square. Okay, so this is the proof of this result. So now onwards, as a standard inverse trigonometric function, the derivative of y is equal to sine inverse x with respect to x is always 1 upon root of 1 minus x square. Okay, so remember this. Now come to the second theorem. Suppose y is equal to cos inverse x. Cos inverse function is defined. So condition on x is minus 1 to 1 and condition on y is 0 to pi. This is domain set, this is codomain set. Okay. Then prove that dy by dx is equal to minus 1 upon root of 1 minus x square. See here carefully. Again by same way we will prove this result. First of all, we have written the given condition here. Just now, as like previous theorem, we have to convert it into x is equal to cos y. So y is equal to cos inverse x can be written as x is equal to cos y. Now we will differentiate this with respect to y. So dx by dy, that is d by dy of cos y. Okay, so we have to take the derivative of cos y with respect to y. So it is very easy. We get it as minus of sin y. Okay. Now by similar adjustment, here we have to write, see here, original derivative is minus sin y. Okay, but we will convert it as like this. Keep this minus sign as it is, and in bracket we will write it as plus or minus under root sin square y. This is just an adjustment here. Okay. Now by fundamental identity, this can be written as minus of in bracket plus or minus root of 1 minus cos square y, and hence we get this minus as it is in bracket plus or minus root of 1 minus x square. Okay. Now this minus sign remains as it is. Okay, and in bracket it becomes plus or minus of this, and we have to decide whether it is plus or minus depending on the condition on y. Means we have to think about sin y. Minus sign keep as it is, just think about sin y. So what about sin y? See here, as it is the condition given here, sin y is positive since y lies in first or second quadrant. See here, 0 to pi, 0 to pi by 2 first quadrant and pi by 2 to pi is second quadrant. So y lies in which quadrant? First and second quadrant. First or second quadrant. So in first or second quadrant, sine function means sin y is always positive. All of you know this. So here if you keep this minus sign as it is, and if you think about sin y only, then sin y is always positive, means this bracket, the quantity in the bracket is always positive. Here we have written it as plus or minus, okay, but we have to write it as plus only. See here, this minus sign is as it is, remember, this minus sign is as it is. We have to think about this only, because we have written here it is minus sin y, but we are thinking about sin y only, not minus sin y. Okay, so minus as it is, and plus or minus in place we have to write plus only. So what about this? Mathematically it is just dx by dy is equal to minus of root of 1 minus x square, because minus into plus is minus. So finally we get dx by dy is equal to minus of root of 1 minus x square. This is the derivative of x is equal to cos y. Okay, now we need the derivative of its inverse. So by that theorem, it is dy by dx is equal to 1 upon dx by dy, and hence we get dy by dx is equal to minus of 1 upon root of 1 minus x square. Okay, so remember this also. So this adjustment is very important, okay, and the condition is important here. So if you remember that, then it is very easy that dy by dx is equal to minus of 1 upon root of 1 minus x square. Okay, now next, tan inverse x. Next function is y is equal to tan inverse x, where x belongs to R, means this is the domain set is R, and codomain set means condition on y is minus pi by 2 less than y less than pi by 2, strictly less than, because minus pi by 2 and pi by 2 are not included. Then the derivative of tan inverse x is 1 upon 1 plus x square. Okay, that we have to prove. Again by same way, first of all we have written the given condition, that is y is equal to tan inverse x and x belongs to R and minus pi by 2 less than y less than pi by 2. Now we can write it as x is equal to tan y. Okay, so the procedure of the theorem is same as the previous theorem. So remember, x is equal to tan y. Now differentiate this with respect to y. So what will you get? So dx by dy is equal to d by dy of tan y, derivative of tan y with respect to y. All of you know that it is sec square y. So dx by dy is equal to sec square y. Now further adjustment, this can be written as 1 plus tan square y. Very simple. 1 plus, just 1 plus tan square y by fundamental identity. So we get dx by dy is equal to 1 plus x square. Very simple. Here don't bother about plus or minus sign. Here just the conversion of sec square y. Directly it is converted into 1 plus tan square y, and directly we get 1 plus x square. Okay. So dx by dy is equal to 1 plus x square. Since tan y is equal to x, here tan y is x, so that's why here it is x square. Now again by that theorem, we have dy by dx is equal to 1 upon dx by dy, and hence dy by dx is equal to 1 upon 1 plus x square. So this is the derivative of tan inverse x. So in this lecture we have studied the derivatives of sin inverse x, cos inverse x, and this is tan inverse x. In our next lecture we will derive, or we will prove, the derivatives of cot inverse x, sec inverse x, and cosec inverse x, depending on the given condition. Okay, so remember all these derivatives as the derivatives of standard inverse trigonometric functions. Okay, I hope you have understood all these three proofs of the theorems. Okay, thank you.